A-Level Mechanics, Centres of Mass, an introduction and a look at compound bodies. Let's have a look and see what we mean by the centre of mass. In static problems or problems involving linear motion, we can usually regard all the mass of an object as being concentrated at one point, which we call the centre of mass. Now this is not true if the body is rotating. If we have a solid body, each atom within the body is attracted by gravity. From a mathematical viewpoint, it's easier if we can consider the total force as acting at one point. If we suspend a lamina from different points on the lamina, and a vertical line is drawn down the lamina, it's found that all such lines intersect at a common point. The total mass of the object acts as if it was situated there. We call this point the centre of mass or the centre of gravity. For some objects it's quite obvious where the centre of mass is located. For a circular lamina it'll be at the centre of the circle. For a rectangular lamina it's where the diagonals cross, halfway along the length and halfway across the width. In other shapes, the position of the centre of mass is not so obvious. For a triangle, the centre of mass is the median of the triangle. That is the point where the lines from each corner of the triangle to the midpoint of the other side meet. We can see this by thinking the triangle is made of many thin strips parallel to one of the edges. Then the triangle would balance on a beam along the median line, as the beam would be under the midpoint of each strip. And since the triangle would balance on each median line, the centre of mass must be at the median of the triangle. For most shapes we need to calculate the position of the centre of mass. Let's look at how we can find the centre of mass of a compound body. That is a body made up of several components. Let's consider an example. Consider a light rod with different masses attached along its length. It's got masses of 1 kilogram, 5 kilograms and 4 kilograms at distances 0.4 meters, 0.7 meters and 1.5 meters respectively along the rod. Find the centre of mass of the combined body. Well, to solve it, suppose we can balance the rod on a pivot. Let the pivot be x meters from one end, and then we can take moments about the pivot. Taking the anti-clockwise moments, we first have a 1 kilogram weight, that's 1 g, acting at a distance of x minus 0.4 meters from the pivot. So that's 1 g times x minus 0.4. Also, we've got a 5 kilogram weight, that's 5g, acting at a distance of x minus 0.7 meters from the pivot. So that's 5g times x minus 0.7, and that's equal to the clockwise turning moments. Now we have a mass of 4 kilograms, that's 4g, at a distance of 1.5 minus x meters. So that gives us 4g into 1.5 minus x. Now we can divide all the way through by g, and then we can expand the brackets, and that gives us x minus 0.4 plus 5x minus 3.5 equals 6 minus 4x. Well, if we get all the x terms on one side and the number terms on the other side, we have x plus 5x plus 4x equals 6 plus 0.4 plus 3.5. which gives us 10x equals 9.9, or x is equal to 0.99 meters. Now this means the centre of mass is 99 centimeters from the end of the rod. This could have been done more easily by taking the moments of the rod about one end. So if we take moments about A, for the clockwise turning moment, we've got 1 kilogram, that's 1 g, at a distance of 0.4 meters from A. That is 1 g times 0.4. Then there's a mass of 5 kilograms, which is 5g, at a distance of 0.7 meters from A. That's 5g times 0.7. And finally there's a 4 kilogram mass, which is 1.5 meters from A. So that's 4g times 1.5. Now that simplifies to give the clockwise turning moments as 0.4g plus 3.5g plus 6g, which is equal to 9.9g. So we have the clockwise turning moment is 9.9g. We can now draw the rod with the 3 masses drawn at one point, that is, at the centre of mass. And that gives us 10 kilograms at a distance x from A. So, if we take moments about A, we've got the clockwise turning moment is 10g times x. But whichever way we do it, we should get the same clockwise turning moment. So that gives us 10gx is equal to 9.9g. And if we cancel the g's, we get 10x equal to 9.9. Well, if we divide by 10, that gives us x is equal to 0.99 meters. And so we get the same answer. The centre of mass is 99 centimeters from the end A. Let's see if we can derive a formula to find the centre of mass of a compound body. That is, a body made up of several parts. To do this, consider several particles of mass m1, m2, m3, and so on up to mn, spread along the x-axis at points x1, x2, x3, and so on up till xn. Then the clockwise turning moments about O, the origin, are given by m1 x1 plus m2 x2 plus m3 x3 and so on up to mn times xn. Now this can be written as sigma, that is the sum from s equals 1 to n of ms times xs. Now, if we consider all the masses having a combined mass of capital M at position x bar, where x bar is the original centre of mass, then the clockwise turning moments would be capital M x bar. But the combined mass, capital M, is the sum of all the small masses. So that's sigma, the sum of, from s equals 1 to n, of ms, which is multiplied by x bar. Now the clockwise turning moments in either case are the same. So we have the sum of the masses times x bar is equal to the sum of the products of ms times xs. And if we divide through by the sum of the masses, we get x bar is the sum of the ms xs terms over the sum of the masses. For short, we can write that as x bar is equal to sigma mx over sigma m. And this is our formula for the centre of mass. Let's have a look at an example. Example 2. Find the centre of mass of the following particles with masses 3 grams, 5 grams, 7 grams, 2 grams and 3 grams at positions 4, 7, 12, 8 and 11 respectively on the x-axis. Well, to solve this we have x bar, where x bar is the coordinate of the centre of mass, equals the sum of the mx's over the sum of the m's. So x bar is equal to 3 times 4 plus 5 times 7 plus 7 times 12 plus 2 times 8 plus 3 times 11 all over the sum of the m's, 3 plus 5 plus 7 plus 2 plus 3, and that gives us x bar is equal to 12 plus 35 plus 84 plus 16 plus 33 all over 20. That is 180 over 20, which is 9. And so the centre of mass is 9 on the x-axis. So far we've found a formula for finding the centre of mass of several particles lying along the x-axis. However, we can extend this into 2 or even 3 dimensions. Consider several particles with masses m1, m2, m3 up to mn with positions x1, y1, x2, y2, x3, y3 up to xn, yn respectively. We can draw a diagram of this. If we take moments about the y-axis, then the turning moment of each particle is its mass times its distance from the y-axis, that is, its x-coordinate. So, the turning moments are m1x1 plus m2x2 plus m3x3 and so on, plus mnxn. So the turning moment is the sum of the mx's, sigma mx. Now, if we consider all the mass at the centre of mass, x bar, y bar, we get the turning moment is capital M x bar, where capital M is the sum of the masses. In other words, the turning moment is equal to the sum of the masses times x bar. Now, it doesn't matter whether we take the particles individually or all grouped together, the turning moments will be the same. So, the sum of the m's times x bar is equal to the sum of the mx's. Sigma m times x bar equals sigma mx. So, x bar is equal to the sum of the mx's over the sum of the m's. Sigma mx over sigma m. This is what we had before. Now, if we take moments about the x-axis, we can similarly show that y bar is equal to sigma my over sigma m, the sum of the my's over the sum of the m's. And we can even extend this to z bar equals the sum of the mz's over the sum of the m's. Z bar is equal to sigma mz over sigma m. Let's look at an example. Example 3. The diagram shows a uniform plane lamina drawn on a grid with square size 1 meter. Find its centre of mass. Well, to solve this, draw the axes with the origin at the bottom left-hand corner of the shape. Then, divide the shape into a rectangle A and a square B. Then mark the centre of each. Let each square have unit mass. Then the mass of A is 4, with centre 2, 0.5. The mass of B is 1, with centre 3.5, 1.5. Now x bar is equal to the sum of the mx's over the sum of the m's, which is 4 times 2 plus 3.5 times 1, all over 4 plus 1, which is 11.5 over 5, or 2.3. Y bar is equal to the sum of the my's over the sum of the m's, so that's 4 times 0.5 plus 1.5 times 1, all over 4 plus 1, which is 3.5 over 5, or 0.7. And so we have the centre of mass of the lamina has coordinates 2.3, 0.7.